Okay, so now we're on to the integration stuff for inverse trig functions. So basically more of the same. It's just it's a little bit different because the u is not a term in the square root version. And so here's problem number one. So if we had chosen u as being 9 minus x squared, when we take du, we'd get negative 2x dx. Well, there's no x up here. So that's kind of the first thing that lets you know that maybe I should try something different. So your first thought would be to do this, to take the term in the square root. And when that doesn't match up, and you think, okay, maybe it's the square root of something minus something, or something plus something, then you think, oh, that's one of those inverse trig things. So if you remember, the way these look is you have something like du over the square root of a squared minus u squared. So basically what you have to do is find out what a is. That's an a, not a 9. So a lot of times these problems, this number is a perfect square to make it easier for you. So you have to not only pick a u, you have to determine an a as well. So step one, we pick u, which in this case is x, and a, which is equal to 3. It's 3 because 3 squared is 9. So we don't have to do anything with that right now. We just hold on to it for later. But we do our second step, which is calculate du. And in this case, it's just dx. And like we've done previously, we're going to rewrite the original expression. And we look here and we say, okay, dx is du, so everything's great. And what we'll do is we'll factor out the 5, which is just a constant. So we'll have dx, which is du, divided by the square root of a squared minus u squared. So at that point, we should be able to go to the table that we have, this big table, 383, and we look down there and we say, okay, do we have that? Oh, yeah, there is. Equation number 18. So we do the integration with respect to u and a. We're really integrating with respect to u. A just comes in there. So we get 5 times the integral. And we look there, and that's the arc sine of u divided by a. And then we had an arbitrary constant at the end. So now, again, like normal, in this case we have to substitute both u and a back in. So we get 5 times the arc sine of u, which is x, divided by a, which is 3. And then we add c. And that's our answer. Okay, our next problem is problem number 4. And we have the integral of 4 over 1 plus 9x squared times dx. So, again, you may think, well, let me let this be u, the denominator. But if you take the derivative, you would get 18x dx. And we don't have an x here. So because of that absence of the x, then we have to try approach B. And also we have to make sure there is something that looks kind of like that. So we go to page 383. We look down at the bottom, and we see that equation number 19 has a squared plus u squared. So there's no square roots involved. And the result is going to be something to do with the arctangent. So we identify u, which is, this part is u. So u is equal to, actually, u squared. So we say u squared is 9x squared. Therefore, u is equal to 3x. So if you take 3x and square it, you get 9x squared. We could also say a squared is equal to 1. Therefore, a is equal to square root of 1, which is 1. Step 2, calculate du. Du is equal to 3 times dx. We have 4 dx, but what we would do is we'd factor out the constant first. So we have dx. So we'd solve this for dx. Dx is equal to du divided by 3. Step 3 is to substitute into this expression. So we have 4 times the integral of dx, which is du divided by 3. And then we have 1 over a squared plus u squared. A squared is 1, u squared is 9x squared. We factor out the 3 constant that's in the denominator, and that leaves us with this, du over a squared plus u squared, and that is exactly what we see in equation 19 on page 383. So step 4 is to integrate. So we have our constant, the integral, look in the book, 1 over a arctangent of u over a. And we add our arbitrary constant c. Step 5, substitute a and u back in. So we get 4/3 times 1 over a, which is 1. The arctangent of u, which is 3x, divided by a, which is 1. C, and then we get rid of stuff we don't need. So we can multiply 4/3 times 1, so it's 4/3. The arctangent of 3x plus 3x divided by 1 is 3x. And before I get going too far here, let me just make sure I'm doing everything right. I'm pretty sure I am at this point. So later on I have to worry about it. Okay, so that's good. Next problem. 12. So let's see what we got here. Yeah, so we've done the arctangent, the arc sine. So we need an example using the arc secant, I guess is the one. So number 12 fits the bill. So we get 1 over 1 or x times the square root of x to the 4th minus 4 times dx. Again, if you chose this to be u, the derivative would be 4x cubed, and we don't have 4x cubed around there. So then we would say, okay, let's try one of these inverse trig functions. And we look in page 383, and we look down to see if there's anything kind of looks like that, and there is. Number 20 sort of looks like that. So we need to get this to look exactly like that with some constants out front. So we know u squared is equal to x to the 4th. So if you take the square root of that, you'll get x squared. And a squared is equal to 4. So a is equal to the square root of 4, which is 2. Step 2, calculate du. So we don't take the derivative here, we take the derivative there. So we get du is equal to 2x dx. Okay, now, what do we do? Okay, so u is equal to x squared. You think, well, I've got x there, but the thing is that when we substitute in for du, well, when we substitute in for dx, dx is going to be equal to du divided by 2x. So that will give us another x here to get this to fit into the form. So step 3 is we substitute. So we get 1 over x times the square root of u squared minus a squared times dx, which is du over 2x. So it's a little more complicated because we've got one additional step. So if I factor out the 2, so I get 1/2, I'll end up with 1 over x squared times the square root of u squared minus a squared times du. But x squared is equal to u, so I can now rewrite this as 1/2 the integral of 1 over u square root of u squared minus a squared times du. So that's exactly what we need. That's equation number 20. And just trying to think if there's another way that you could do this. Yeah, the other way of kind of looking, I was trying to think if there's another way of approaching this, which would leave out a step. The other way to solve this is we'd say, what is dx over x? Well, if we divide, is that right? Dx over x. No. Yep. Yeah, no, I think that's the only way to do it. I was trying to think of an easier way to think about it, but I couldn't come up with anything. You just have to recognize that when you've got this extra term out here, it's so slightly different. Okay, so step 4 is integrate, which means just look it up in the book. So the integral of 1 over u squared of u squared minus a squared is equal to 1 over a the arc secant of the absolute value of u over a. And then we add an arbitrary constant. And then we substitute. So we get 1/2 times 1 over a. A was equal to, let's see, what did we had a equal to? 2. So we get 1/2 the arc secant of the absolute value of u, which was x squared, divided by a, which is 2, plus c. And so the final answer is 1/4. 1/2 times 1/2 is 1/4 the arc secant. Now, because I'm squaring this, I can remove the absolute value signs, because if I square something, it's always positive. So I can just say it's x squared over 2 plus c. So this was problem number 12, and the answer is 1/4 arc secant of x squared over 2 plus c. So that's right. So they did take out the absolute value signs just like I did. 14. 14 is equal to, well, we want to find out what the integral of 1 over 3 plus x minus 2 squared dx. So this is a little bit different because we don't just have x squared raised to the 4th. But it's in the form of the inverse tangent because there's no square roots involved. So it is going to be an inverse tangent thing. And so, again, if we took the derivative of the whole denominator, we wouldn't match up with the numerator. So that wouldn't work out. So what we're going to do is we're going to let u equal, or u squared equal x minus 2 squared. Therefore, u is equal to x minus 2. And a squared is equal to 3. So a is equal to the square root of 3. It's just a positive square root. So with that substitution, then we take the derivative of u. So du is just dx, because this goes to 0. So then we can make our substitutions into the original equation. So we have the integral of 1 over 3, which is a squared, plus u squared times du. We integrate, meaning we look in the book. And so I go to page 383, the arc tangent. So the answer here is 1 over a times the arc tangent of u over a plus c. Step 5 is we substitute in. So we have 1 over the square root of 3 times the arctangent of u, which is x minus 2, divided by a, which is the square root of 3, plus c. And the only thing we would do is we don't like to have a radical in the denominator. So the first term would end up become the square root of 3 over 3 by multiplying both the numerator and the denominator by the square root of 3. And probably the same would be true here. So we'd end up with the square root of 3 times x minus 2 divided by 3. And then another arbitrary constant. And actually they didn't. They just left it as 1 over the square root of 3. But, so, not sure why, but they did. Okay, where are we? We just did 14, I think, so now we're going to go to 18. So this one's a little more complicated. So here we go. Now, notice that if you let that be u, you get negative 2x dx. Sort of matches up with that, but you got this extra term. So a lot of times when you have a common denominator and two terms, you need to break it up into two separate integrals. So that's what I'm going to do. So this is equivalent to doing this. Okay, so it's pretty easy. Just take that as one term, the second term. So we're going to treat these exacts completely differently. This one, we're going to let this be u. So the derivative is going to be negative 2x dx. So you've got x dx. Here we're going to let u equal x and a equal 1. And then we'll end up with an inverse sign. So this one's going to end up being square root of 1 plus x squared. In the numerator, when we integrate it, and this one's going to be 2. So let's just do them separately. So the first one we'll do is this one. I'm going to use u for both of them because I'm doing it separately, so that's kosher. So this one, I'm going to let u equal, step number 1, choose u is equal to 1 minus x squared. 2 du negative 2x dx. Factor out the 4 from the original equation. So I have x dx, so I need to solve for x dx. X dx is equal to du divided by negative 2. So now I can make the substitutions. So my original function becomes 4 times x dx, which is equal to du divided by negative 2. And I get 1 over the square root of u. So I'll factor out the negative 2, so I'll have 4 divided by negative 2. Integral of u to the minus 1/2 power du. So I've changed that to the half power and then moved it to the numerator. So then I integrate. So 4 divided by negative 2 is negative 2. And then the integral is going to be u to the 1/2 divided by the new exponent, which is 1/2, plus c. So this becomes that. This integral, add 1, divided by the new exponent. Dividing by 2 is like multiplying by 2. Dividing by 1/2 is like multiplying by 2. So I get negative 4 u to the 1/2 plus c. Step number 5 is substitute u back in. So we get negative 4, 1 minus x squared to the 1/2. Or we could write that as negative 4 times the square root of 1 minus x squared. Okay, so that's the first integral. The second integral was negative. It was negative the integral of 3 dx over the square root of 1 minus x squared. So in this case, same steps, but a little slightly different because we're going to let u equal u squared is x squared. Therefore, u is equal to x. A squared is equal to 1. Therefore, a is equal to 1. So those are the substitutions, except now we need to substitute for dx. Well, du equals dx. Just the same thing on either side. So now we can make substitution. So I'm going to factor out the negative 3. So we get negative 3 times dx, which is du, divided by the square root of a squared minus u squared. So we can go back and look on page 383. We see that the integral of du over a squared minus u squared is equal to the arc sine of u over a plus an arbitrary constant. The arc sine is a weird one because it doesn't have 1 over a in front of it. The other two do. And then step 5 is substitute in. We have to substitute in both the u, which is x, and a, which is 1. And so we can simplify that. Negative 3 arc sine of x plus c. So the final answer, if we go back to the original expression here, so that's what we were doing. So that integral, oops, push the wrong button there. What did I want to do? Oh, paste, not save. Okay, must have done something wrong here. Okay, copy, paste. Okay, there it is. So now we just do the two parts. Well, we know the second part is negative 3, the arc sine of x. We have our arbitrary constant, which we just combine them into 1. And the other one was negative 4 square root of 1 minus x squared. So we have negative 4 square root of 1 minus x squared. And that should be it. So let me just check my answer, which that's problem number 18. Negative 4 square root of 1 minus x squared. They have plus sine. Oh, did I write something wrong down here? No, I just wrote the problem down wrong. Okay. This is plus. This is plus. So that's plus. And keep going along here. That's plus. That's plus. 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 Done. Okay, we're at problem 23. So the only difference here is that they're definite integrals. So we are going to just have that extra step of changing the limits of integration. So 23 is the integral from 0 to the square root of 3 over 2, 1 divided by 1 plus 4x squared dx. So this is like the arctangent, so one where there's no square root. So we're going to let u squared is going to be equal to 4x squared, therefore u is equal to square root of 4 is 2, square root of x squared is x. A squared is equal to 1, therefore a is equal to 1. Step 2, calculate du. du is equal to 2 dx. And in this step, we'll also redefine the limits of integration. So when x equals 0, u is equal to 2 times 0, which is 0. When x equals the square root of 3 over 2, u is equal to 2 times the square root of 3 over 2, which is equal to the square root of 3. So then we can make substitution. Step 3, substitute. The integral limits go from 0 to the square root of 3. We have dx, we'll go back here, dx is equal to du over 2. So we'll get 1 over a squared plus u squared times du, which is, or dx, which is du over 2. We'll factor the 1/2 out. So we just get du divided by a squared plus u squared. Go to the book, look that up. You find out the integral is 1 over a times the arc tangent of x over a. X is 2x. X is 2. U is 2x, and then we divide by a, which is 1. And because it's a definite integral, we go from x. Well, actually, we don't have to. What am I doing here? Okay, get carried away. So you get u over a. I knew something was wrong. So, and we integrate that from u equals 0 to u equals square root of 3. Now I have to plug a in. So I get 1/2. A is 1, so it's just going to be 1 over 1, which is 1. So we get the arc tangent of just to u. From u equals 0 to u equals square root of 3. So well, that was the integration part. So that's step number 4 right here. Integrate. Step number 5 is to evaluate the integral. So we get 1/2 the arc tangent of the square root of 3 minus the arc tangent of 0. So you can just plug that in your calculator. You'd use, calculator terminology. We'd use the inverse tangent function. And if you remember, you can use I'll use my calculator here in a second, but remember the tangent has values of 0, the square root of 3 over 3, 1, the square root of 3, and infinity. So, and that's 4, 0, pi over 6, pi over 4, pi over 3, and pi over 2. So those are the corresponding values. So you can see that the angle whose tangent equals the square root of 3 is pi over 3. So you plug in your calculator, and the inverse tangent of 0 is 0. But if we didn't know that, we can take 1/2 times, now we use parentheses, inverse tangent of the square root of 3 minus the inverse tangent of 0, and I get, oh, what did I do wrong here? Oh, I did something wrong here with my 0 didn't come out. I pushed a point. Okay, tangent of 0. And so you plug those in, and you get 0.5236. I get point. Yeah, okay. You get 1/2. This is also, if you do it using this thing, you get 1/2 times pi divided by 3. And if you take 0.5 times pi divided by 3, you get 0.5236, which is exactly what I got. Just plugging into the calculator. Okay, problem 25. So this is actually a little different. Okay, so we have the integral from 1 divided by the square root of 0 to 1 divided by the square root of 2, which is the same as the square root of 2 over 2. Okay, so we have the arc sine of x divided by the square root of 1 minus x squared dx. So it's not going to work choosing u equal to x, because when you've got this arc sine function on the top. So that's not going to work. You can't pick this whole thing as being u, because you're just going to end up with minus 2x dx. So the thought would be, let's try the other thing. What else do we have left? We have the arc sine of x. So we would take the derivative of that, and the derivative of the arc sine is 1 divided by the square root of 1 minus x squared dx. Ta-da! So this is u. This is du. So when we make the substitution, let's also redefine the limits. So when x equals 0, u equals the arc sine of 0, which is equal to 0. It's the same as the inverse sine of 0. If you plug that into your calculator, you get 0. When x equals 1 divided by the square root of 2, u equals the arc sine of 1 over the square root of 2, which is also, if you multiply and divide by the square root of 2, you get the square root of 2 over 2. Hopefully that looks familiar. It's 45 degrees, or the angle u is equal to pi over 4. If you just plug that in your calculator, if you did the inverse sine of the square root of 2 divided by 2, you get 0.7853. Makes it 7854, if you round off correctly. And if you take pi and you divide by 4, you get 0.7854. So it is that. And if you wanted to rewrite this in terms of pi, you'd multiply it by pi and divide by pi. So you take this divided by pi and you get 0.25, which is a quarter. Okay, so those are my new limits. So now I can make the substitution. So my substitution is I have my new limits, which are from 0 to pi over 4. My u is the arc sine. My du is dx over square root, so it's just times du. So I integrate this. This complicated thing just turns out to be a simple polynomial. So you get u squared over 2. And you evaluate that between 0 and pi over 4. So the 0 squared is 0, so all you have to do is evaluate it at the upper limit. So you end up with pi over 4 squared minus 0 squared, and so you get pi squared over 16. Okay, what did I do wrong here? Oh, I know what I did wrong. This should have been 2. Is that right? No, that's right. So I'm missing a half somewhere here. Did something wrong. Oh, okay. I forgot the half right there. So it's actually over 32. I thought I did something wrong earlier. So 4 squared is 16 times 2 is 32. So that's the integral. This is the integral, original integral. Pi squared over 32. And if you calculate that out, it just comes out to 0.308. Okay, so we're continuing on. Section 7. What problems do I have left here? 6. So it's a new day of recording. I'm going to go ahead and finish these up. I'll have them all done for semester, and I think I have to write that as the exam. Okay, I got this about ready. Okay, so we're on, this is problem number 30. And let's just write it down. It's a definite integral. It may not look like it originally fits in one of these inverse trig forms. It's kind of interesting because it's a trig, it involves trig functions, but we're actually going to use the inverse trig integration. So let's just think about it. You know, if I were trying to put this into the logarithm type integration, 1 over u du, I would let this be u. And the derivative of u would be, well, I have sine of x squared, which when you take derivative of that, it would be 2 times the sine of x times the cosine of x using the chain rule. Well, all I have is cosine of x dx in the numerator, so that wouldn't work. A lot of times, if you have a term that's squared, except for the one we just did in class today, but anyway, if you have something squared here by itself plus a constant, a lot of times that means it's going to be involved the inverse tangent of the arctangent. If the derivative of u, say u is going to be u squared would be the sine squared of x, then u is the sine of x. So the derivative of the sine is cosine. So that's going to work out. So it does fit. We'll see. So I'm going to let u squared equal the sine of x, sine squared of x. Remember that the sine squared of x is the same as the sine of x quantity squared. So, okay, a squared is going to be 1, which is its constant. So a is the square root of 1, which is 1. And this step now includes identifying u squared, but then you have to calculate u. So the square root of something squared is just something. So u is the sine of x. Step 2 is to calculate du. You know, the rest of the stuff up here has to be du. So du is the derivative of the sine of x, which is the cosine of x dx. And you can see I have the cosine of x dx, so I can make that substitution. I can substitute du for the cosine of x dx, and I can substitute sine squared as u squared, and I can put a squared as 1 squared. Now, because this is a definite integral, I'm going to go ahead and change the limits at this point. So when x equals 0, u equals the sine of 0. So use the sine of x, so I plug in x equals 0 to there, and the sine of 0 is 0. When x equals pi over 2, u equals the sine of pi over 2. And the sine of pi over 2 is 1. Again, you just plug it into your calculator. Make sure you're in radians. Hopefully you remember that the sine of pi over 2 is 1, the cosine of pi over 2 is 0. But in case you didn't, you can use your calculator. So now step 3 is the substitution stuff. So we're going to substitute it back in here. We're going to substitute for the terms that involve x. We're also going to substitute in the limits. So the original equation becomes the integral from 0 to 1, because u goes from 0 to 1, whereas x went from 0 to pi over 2. The cosine of x dx is du. So this part becomes du. And we divide by 1 plus, this is a squared. So let's put a squared. I should have done that. So 1 is a squared plus sine squared of x is u squared. Okay, so now we say, do we have it? Does that fit the any of those formulas on page 3 exactly? Look here, it kind of looks like number 19. So since it looks exactly like number 19, we can just do the integration, which means look it up at the table. So we get 1 over a times the arc tangent of u over a plus c. Now, step 5. Actually, that's not true. We have to. It's a definite integral. So we evaluate it at from u equals 1 to u equals 0, u equals 1. Those are limits. Okay, now we substitute. Well, actually, we don't have to substitute back in. The only thing we have to substitute is a, because we're going to keep it in terms of u. So we don't have to go back and substitute it back in because we're not finding an equation. We're finding a number. So let's go ahead and substitute a in. So let's say for a definite integral, that's what we're doing. Substitute a only, because we're just going to leave it in u. Now, if we were an indefinite integral, we'd substitute a and u. Okay, a is 1, so we just get the arc tangent of u, where u is between 0 and 1. So our step 6 here is now just to plug the numbers in, evaluate at the upper limit and subtract evaluating at the lower limit. What does that mean? It just means plug the numbers in. So you have the arc tangent of 1 minus the arc tangent of 0. 1 and 0. Well, the arc tangent of 1, the angle whose tangent is 1 is pi over 4. And the angle whose tangent is 0 is 0. So the answer is pi over 4. And next I'm going to look these answers up. Not that I don't trust myself, but I just don't want you to. There's always chances for mistakes, and I've been a little arrogant, but I'm not really arrogant, but I keep thinking I'm just not making mistakes, which is definitely a possibility. So number 30, the answer is pi over 4. Okay, so that's correct. So nothing new. The only difference here is that we did start off by defining u squared and a squared, calculating u and a here, calculating du, looking back at the original equation, saying, do we have exactly what we have here, cosine of x dx? In this case, we do, so we don't have to rearrange this. We don't have to solve for whatever's in here. We have a constant, extra constant or something. Because we're doing a definite integral, we rewrite the limits of integration. Then we make the substitutions, which includes the limits as well as all the variables. And so we come up with this integral, which is an integral that is on page 383. We look up the formula, write it down. In this case, we don't have to substitute u and a back in. We just have to substitute a back in because we're evaluating the integral at the limits in terms of u, so we don't need to rewrite it just like before. So we plug a back in, which a was equal to 1. So we just get the arctangent of u evaluated between 1 and subtracted, evaluating it 0. And the arctangent of 1 is pi over 4, and the arctangent of 0 is 0. And again, if you plug these in your calculator, if you did the arctangent of 1, what you would get is some number, but we always want to convert back to radians. We're going to use the calculator. If you want to use the unit circle, that's fine. But if we do let me make sure I'm in radian mode. I wish that would show up somewhere so I didn't have to look. But anyway, so we do the second tangent, or inverse tangent of 1, and I get 0.7. So if I did it on my calculator, I would get 0.7854 minus, if I do the arctangent of 0, I get 0. And what I would do is I would take this fraction for this decimal and multiply by pi and divide by pi. And so this is the term in the parentheses is what I plug in my calculator. So I already have the inverse tangent of 1, which has all the decimals. And I divide by pi, and I get 0.25. And 0.25 is a quarter, so I get pi over 4. So that would be the calculator way. This would be the unit circle way, if you want to use it. Okay, the next problem is 34. So this begins the place where we have to rewrite them in terms of completing the square and also taking each part. So these get a little complicated. So let's just write it down. So we get 2x minus 5 divided by x squared plus 2x plus 2 dx. Now, when you see something like this, notice that the whole denominator is not squared. So you might think natural log. But that only works if the numerator is exactly equal to the derivative of the denominator. And sometimes it is and sometimes it isn't. So, but we can take this and make it into two fractions. One where we're going to have this as the denominator, and the second one where we're going to rewrite this as a complete square plus a constant. The one where we have the whole denominator, that's the natural log part, and when we make it a complete square, that's going to be the in this case the inverse tangent, because we don't have a square root involved. So let's just think about this. So if I took the entire denominator and I took the derivative with respect to x of that, what is it? Well, you know, these are all x's and constants, and I'm taking the derivative with respect to x, so it's just normal derivative. So I get 2x plus 2. And if I look at my original equation, I've got 2x minus 5. So what I can do is I can say that 2x minus 5 is equal to 2x plus 2 minus 7, because 2 minus 7 is negative 5. So these are equivalent to each other. So I can combine these two and make that one numerator, and I can have another fraction where this is the numerator. So my original integral is going to be 2x plus 2 minus 7 divided by x squared plus 2x plus 2 dx. And you can do this in one step. I'm just doing it too, so it's entirely clear. And make sure I push the record button. I don't want to take any chances here because it takes a long time to do these problems. I don't want to make a mistake. So you get the first this term here, which is what I have in parentheses here, and then you have a negative 7 dx divided by x squared plus 2x plus 2. Now this one's going to fit the natural log, because if I let u be this, then du will be that. And so I'll get du over u. Okay, we'll do that later. This one is going to involve the inverse tangent, because I'm going to have x squared. I'm going to have x plus something, quantity squared plus another constant. So I have to take this and make this into involving complete square plus a constant. So let's just do that separately. So if we have x squared plus 2x plus 2, that's the same as x squared plus 2x. I'm going to put the plus 2 over here to a little bit further. So what I want to do is take the ones that involve the variable, the two terms that involve the variable x, and I want to add a third term, which I then can make into a complete square. So to do that, you always take the coefficient associated with the variable raised to the first power, 2. You divide by 2, and then you square that. Well, that's 2 divided by 2 is 1. 1 squared is 1. So I add 1 here, and I subtract 1 there. So by adding and subtracting 1, I'm not changing anything. Now, this can be rewritten as a complete square. So the complete square is always x plus or minus something, and that something is this term right here, is the one we had before we squared. So we're going to take x plus 1, square the whole thing, and then our two constants end up being just plus 1 because we have 2 minus 1. So we can say that x squared plus 2x plus 2 is equivalent to x squared, quantity x plus 1 squared plus 1. So the second part of this integral can be rewritten as 7 divided by x plus 1 quantity squared plus 1 dx. So these two things are equivalent to each other, but now it's in a form where I can let this be u and this be a, and this can be u squared and this can be a squared. So I'm going to do these each one separately now, and then we'll combine them again. So let's take the first part, and we're going to use u substitution. So the first of those two integrals was 2x plus 2 divided by x squared. What was it? X squared plus 2x plus 2. X squared plus 2x plus 2 dx. So what we're going to do is step 1. U is equal to the whole denominator. Step 2, calculate du. 2x plus 2 times dx. So I have, and then I go back to my original equation and say, okay, do I have everything I need here? I have 2x plus 2, whole thing times dx, so it matches up exactly, so I can make a clean substitution, and I can put u in there. So step 3 is to substitute back into the original equation and make it into something that I can integrate. Look on page 383. So the numerator becomes du, the denominator becomes u. Step 4 is to integrate, so that always means do I have the exact equation looking in the book. So I look through there and I say, okay, number 5. Equation number 5 on 383 says the integral of du over u is the natural log of the absolute value u. So natural log of the absolute value u equals c. And step 5 is to substitute natural log of the absolute value u, which is x squared plus 2x plus 2 plus c. So that's the answer for the first part. Then we have the second part, which is this one. So let's do that. So I'm going to say negative the integral of 7 divided by the quantity x plus 1 quantity squared plus 1 dx. So I think that's right. 7 dx over x plus 1. Okay, so now we do the same thing, but we're going to use the procedure for the inverse trig function. So we're going to let u squared equal x plus 1 quantity squared. We're going to let a squared equal 1. So that's u squared plus a squared. So u is equal to just x plus 1. A is equal to the square root of 1, which is 1. Step 2 is to calculate du. So du is equal to dx, because the root of x is 1 multiplied by dx gives us dx. This goes to 0. So that's du. We look back at the original equation, and we're going to go ahead and factor out the constant. So we end up with du, or dx. So before we do the substitution, I'm going to factor out the constant. Okay, so now we do the substitution. So we have negative 7 times the integral of dx, which is just du from step 2, divided by x plus 1 squared is u squared. 1 is a squared. Do we have a formula that fits that? Let's go to page 383. Look down, we see number 19. And you kind of have to know what you're going for. You can't just wait now. What you really do is, here you kind of look at all the left-hand sides of the integrals. Is there anything that fits there? And then when you do the integration step, you go back and look at the same thing and say, okay, what is the integral of that? So we get negative 7 times. Okay, from page 383, we get 1 over a, the arc tangent of u over a plus c. Okay, I'm just going to put the c out front by itself. And then 5 is we substitute back. Because it's an indefinite integral, we do substitute u and a back in. If it was a definite integral, we would have changed the limits of integration. And the limits would be different depending upon which one of these, whether it was this integral or that. We'd have to change the limits twice, once for this one and once for that one. So you got to be consistent. You can't just do it once. Okay, so we get -7 times 1 over a times the arc tangent of u, which is x plus 1, divided by a, which is 1, plus c. So we get -7 times the arc tangent of x plus 1 plus c. Okay, now combine the two parts. So the first part was this one. So we have the natural log of the absolute value of x squared plus x plus 2. The second part is -7 times the arc tangent of x plus 1. And we just add we combine the two arbitrary constants and make one arbitrary constant. And now we look at the answer. This is problem 34. And 34, the answer is the natural log of the absolute value of x squared plus 2x plus 2 minus 7 times the arc tangent of x plus 1 plus c. So that is the answer right there. So what is that the answer to? Well, it's the answer to what is the integral of this thing to start with. So if you want to go through it again, just let me review it again for you. We take the original equation, we look at the denominator, and we take the derivative of the denominator, which is 2x plus 2. We look at that and go back to the original equation and say, is that exactly equal to? If it was exactly equal to, we wouldn't have to worry about the arc tangent. We'd just say use the logarithm. But in this case, because it's not exactly equal, we rewrite it in terms, the original thing, in terms of this, which is the derivative of the denominator, and some other term. So when we add this and that, we get the original -5. So we rewrite the 2x minus 5 is 2x plus 2 minus 7. Then we break it up into this part and that part. This part where the numerator is exactly the derivative of the denominator, we can rewrite that as d over u. And this one, where we just have a constant, we can take the denominator and complete the square to fit it in a form which is going to be something that we can use the inverse tangent of the arctangent. So the second step was we took the denominator just for this part. We don't want to do it for this part, just for this part. We complete the square so that we rewrite this as a complete square plus a constant, minus a constant, depending upon what we're doing. In this case, it had to be a plus constant, or it wouldn't fit, but later on we can handle a negative sign. So we take this second part of the original integral and rewrite the denominator. And at that point, we can then do the two integrals. So the first integral involved the natural log, where we could take this and rewrite it as du over u. The second part was this, where this was u squared, this is a squared. This is just a constant we can factor out. And once we figured out the individual parts, then we can put them together, and we combine the two arbitrary constants into another arbitrary constant. Okay, our next problem is 37, which is very similar to what we had before. So let us look at it. Just what we just did. It's a little more, well, let's see, it's any more complicated. It's about the same complication. So we're going to break it up into two parts. One is going to involve where this whole term in the square root is u. And to make that work, we're going to have to rewrite the numerator as somehow involving the derivative of this thing, and then we're going to break it up. So, like before, we look at the term in the parentheses. In the previous problem, we just took the entire denominator. But so that we're going to look at that, and we're going to see what is the derivative of that denominator, of the term in the square root. So we get is negative 2x minus 4, which is the same. If we factor out a negative 2, we would get x plus 2. So we look at the numerator, and in this case, actually the whole numerator is this. So it looks like if we let this be, it looks like we might have had to use the inverse trig functions, but in this case, because this matched up exactly, we don't have to. It matches up exactly except it's constant. So it turns out this problem, let me just check to make sure that's true. Okay, yeah, so we don't end up having to use inverse trig functions. Now, if this original equation had been different, and I want to work it both ways just to show you how you would do it the other way. Then you would have to break it up. If this number was anything other than just 2, so this matched up exactly, then we'd have to do something different. So let's just finish this off, and then I'll go back and show you another example. So what we're going to do is we're going to let u equal negative x squared minus 4x. So du is equal to, we just did it up here, negative 2 times x plus 2 times dx. So we go back here. You see we have the quantity x plus 2 times dx. Here I have negative 2 times x plus 2 dx. So I'm going to solve for what I have in the original equation, which is x plus 2 dx. And that's going to be equal to negative du over 2. So I divide both sides by negative 2. So I can make that substitution. This becomes u. So the third step is to rewrite the original equation. And so the numerator becomes du, actually becomes negative du over 2. So let me just put that out back, negative du over 2. And the denominator becomes the square root of u, which is the same as negative 1/2 the integral of du over the square root of u. So this is just a power rule problem. So what is it? So step 4 is integrate. So 4, we have the integral minus 1/2 the integral of u to the minus 1/2 du. What I did is I rewrote this as u to the 1/2 and I moved it to the numerator. So when I integrate this, I add 1 to the exponent, so I get u to the 1/2, positive 1/2. I divide by the new exponent, plus c. And this 1/2 is multiplied to this whole thing. This one's divided by 1/2. So if we just look at the denominator, we have 2 times 1/2, which is 1. So we're just going to end up with negative u to the 1/2 plus c. And step 5 is then just plug, because it's an indefinite interval, we're going to plug u back in, so we get negative x squared minus 4x to the 1/2 plus c. And if we have an exponent of 1/2, we typically rewrite it as a square root. So we'll have negative, the square root of negative x squared minus 4x plus c. And that should be the answer, which it is. Now what I'm going to do is I'm going to make it just a little bit harder. If I took the original equation, and let's say I made that 4. So we have the integral of x plus 4 divided by the square root of negative x squared minus 2x dx. So when we take the derivative, we're doing the same thing here. We take the derivative of the term in the square root sign, we would get negative 2x minus 2, which is the same as negative 2 times x plus 1. Is that right? Did I do something wrong here? Oh, it's 4x squared. Okay. Something's wrong. Okay, so that's 4x. So that'll become 4x, that'll become 4, that'll become plus 2. Okay, so that's 4x, that's 4, and that's 2. Okay, so that's what we had. But what we look at is we see that in the numerator we have negative, we have x plus 4, and the derivative is actually this. So what are we going to do? Well, if we were to factor out a negative sign, I'm sorry, yeah, that's right, okay. If we had, so let us see what we're doing here. Okay, 2x, negative of a negative, so this is going to be, what I'm trying to do is rewrite this in terms of what I have. So, make sure I'm getting it right here. Because I don't want to just, I need to, okay, so the original, this is negative the integral of negative x minus 4 divided by the square root of negative x squared minus 4x dx. So what I did is I factored out a negative sign and made this negative. Okay, so let me do this again. So that's negative, and we have negative x. So if I want to keep this, but I want to get this as my derivative, okay, what am I doing here? Let's see. So if I factor out a negative 1/2, this becomes 2x plus negative 2x. Okay, we'll get this right here. Negative 2x minus 8. It takes a little, obviously I'm not going to do this on a test, but I'm factoring in a negative 1/2. Okay, so now what I'm trying to get is negative 2x minus 4, and what I have is negative 2x minus 8. So I have minus 1/2 times the integral of negative 2x minus 4, and then I have to have another negative 4 to get what I had originally, negative 2x minus 8. Okay, now what we do, let's add one page. I can break this up into two parts. I'll have negative 1/2 times the integral of negative 2x minus 4 over the square root of negative x squared minus 4x, whole thing times dx, and I get negative 1/2 times the integral of negative 4, which is this one, negative 4 dx divided by the square root of negative x squared minus 4x. Okay, so this, if I take the derivative of that, I'll get that. And so I can rewrite this as du over u, the derivative of the square root of u. Now the second part here, which is different, so this is exactly like the first part. Now this is the second part. What I would do is I would have to rewrite this in terms of a complete square. So we're going to go over here, and we're going to take the term in the parentheses. And what I would do is I have to factor out a negative sign. So I have negative the quantity x squared plus 4x. So to complete this square, I would take 4 divided by 2, this number divided by 2, squared. 4 divided by 2 is 2, 2 squared is 4. So add 4. But notice I have 4 and I have a minus sign, so I'm really subtracting 4 because of this negative sign up front. So then I add 4 here, so that this 4, when it's multiplied by the negative sign, cancels out with that. So this becomes negative the quantity x plus 2 quantity squared plus 4, or 4 minus the quantity x squared plus 2 squared. So the term in the parentheses can be rewritten, and so the second integral is going to become negative 1/2. We can actually go ahead and factor out the negative 4. So you have negative 4 times negative 1/2, which would be plus 2, times the integral of dx divided by the square root of 4 minus x plus 2 quantity squared. Oh, I get it. I already had the dx. Now, this fits the inverse sign if we let u squared equal x plus 2 squared, and if we let a squared equal 4, which means u is equal to x plus 2, and a is equal to 2. So we calculate du. Du is just going to be equal to dx, because when we take the derivative here, this just becomes dx, and that becomes 0. So we can now substitute in to the original equation. For dx, we put du. For 4, we put a squared. For x plus 2 quantity squared, we put in u squared. Now, so this is exactly something out of the table. So step 4 is to integrate. So we just write down what's in the table, which is the arc sine of u over a plus c. Step 5 is to substitute back in u, so we get 2 times the arc sine of u, which is x plus 2, divided by a, which is 2. Let's see. So that's the second integral. And the first integral we've pretty much done already. The first integral was where are we? Was this one, which we already did. So anyway, that's how the problem becomes much harder if that happens. Okay, that's 37. We're going to move on to 39, which I think is one where you have to go through the whole thing, and it's a definite integral. So this is probably one of the harder ones that we're going to do. Pretty sure. Yep. Yeah, 45, which is one that we actually did in class. 47 is just, so this is the last hard one. So we have the integral from 2 to 3 of 2x minus 3 divided by the square root of 4x minus x squared dx. So this is like the second part of the last problem. So what did we do? Well, we looked at the term in the square root sign, and we took the derivative with respect to x so we can compare it with the numerator. So we get 4 minus 2x, which is the same as negative the quantity 2 minus 4, 2x minus 4. And you can see in the original equation we have 2x minus 3, so it doesn't quite work out. So what we're going to do is we're going to factor out a negative sign. And usually you have to do that with these square root, these sign things, because we always have minus x squared to make it fit. So then we have negative 2x plus 3. So this becomes negative, that becomes positive. Okay, so let's actually just minus 2x plus 4. So when we have minus 2x plus 3, so if we can rewrite, so what we're going to do is we're going to take negative 2x plus 3, and we want to make it so part of it is the exact term there, negative 2x plus 4. But to get back to 3, we have to subtract 1. So this is the derivative that we're looking for, and then this is the thing that we add on to get back to where we started. So that integral here becomes negative the integral from 2 to 3 of negative 2x plus 4 minus 1 divided by the square root of 4x minus x squared dx. So then we can create two fractions. So we get negative the integral from 2 to 3 of negative 2x plus 4 divided by the square root of 4x minus x squared dx. And then we have negative the integral from 2 to 3 of negative 1 divided by the square root of 4x minus x squared times dx. So this is the part that we're going to solve without using inverse trig functions. This is the part that we're going to solve using the inverse trig functions. So let's do this one first. So we're just going to look at this by itself. These are definite integrals, so we find the definite integral separately and we add those numbers together, then we'll be in good shape. Okay, so that's what we want to do. So step 1, what is u? U is equal to 4x minus x squared. Therefore, du is equal to 4 minus 2x, or negative 2x plus 4. I forgot to multiply it by dx. So that matches up exactly with that. Negative 2x plus 4 dx. I can use du for that, and I can do square root of u for that. So step 3 is substitute, but actually, because it's a definite integral, we're going to redefine the limits. So when x equals 2, u is equal to 4 times 2 minus 2 squared, which is 8 minus 4, which is 4. And when x equals 3, u is equal to 4 times 3 minus 3 squared, which is 12 minus 3, which is 12 minus 9, which is 3. So we're actually integrating from 4 to 3, but we have this negative sign, so we can actually take this and let me just write it out. So you get negative the integral from u equals 4 to u equals 3 of negative 2x plus 4 divided by, actually I'm not, let's go ahead and make substitutions here. So negative 2x plus 4 dx is equal to du divided by the square root of u. And that, if you change the limits of integration, you can get rid of the negative sign. Then you change it becomes a negative of that. So the negative, the integral from 4 to 3 is the same as the integral from 3 to 4. Okay, we did this before. The integral of that is you get, remember that's equal to the integral from 3 to 4, u equals 3 to u equals 4 of u to the minus 1/2 power du. So you add 1, so you get u to the 1/2 divided by 1/2. No, not plus c, because it's not a definite integral. I mean, it's a definite integral. So we go from u equals 3 to u equals 4. Dividing by 1/2 is like multiplying by 2. So our final answer for the first part is 2 times 4 to the 1/2 power of the square root of 4 minus 3 to the 1/2 power, which is the square root of 3. So let's just go ahead and calculate the number. So we have 2 times, turn my calculator on, 2 times quantity 4 to the 0.5 power minus 3 to the 0.5 power. And the number I get is 0.5359. Or you could say it's 2 times 2 is 4 minus 2 times the square root of 3. So another way of doing it would be, this would be 2 2 times 2 is 4, minus 2 times the square root of 3. That'd be another. You didn't want to multiply it out. Just leave it. That terms. Okay, so that's this part. The second part is what is the negative the integral from 2 to 3 of -1 divided by the square root of 4x minus x squared. 4x minus x squared dx. Well, we have to rewrite this as a complete square first, so this will fit the formula. So if we factor out a negative sign, we get that. And then we take -4 divided by 2 quantity squared. So you get -2 squared, which is +4. So we add 4 here. We multiply by -1, so we're really subtracting 4 from the equation. So we have to add 4 again. So 4 times -1 is -4. Plus 4 is 0, and we get back to our original expression. So this, now we can rewrite those 3 terms as a complete square, x minus 2 quantity squared, plus 4, or you can say it's 4 minus x minus 2 quantity squared. So the term in parentheses we can rewrite, and let's get rid of the negative signs. So negative times negative is a positive. So we get the integral from 2 to 3 of dx divided by the square root of 4 minus x minus 2 quantity squared. So now we can integrate it because it's in a form that at least looks similar to what we should get. And so we'd say u squared is equal to x minus 2 squared. A squared is equal to 4. So this is u squared, this is a squared. So u is equal to x minus 2, and a is equal to 2. Now we calculate du. Du is just dx. Derivative of u is du. Derivative of x is dx. We're going to redefine the limits again, so they're not the same as last time. So when we let x equal 2, u is equal to 2 minus 2, which is 0. And when we let x equal the upper limit, which is 3, u is equal to 3 minus 2, which is 1. So we can take the original expression now, making all these substitutions, both for u squared, a squared, and du, as well as changing the limits. So the original integral becomes the integral from 0 to 1, instead of from 2 to 3 becomes 0 to 1. And dx is du. The denominator is a squared minus u squared. Okay, so there you are. That's the formula. So that's step 3 is substitution. 4 is integration. So we go to page 383, and we see that the integral of this is the arc sine of u over a. We don't add the arbitrary constant because we're going to evaluate it between u equals 0 and u equals 1. I didn't change the order of integration because it's already positive. So and I also have a larger number at the top and smaller number at the bottom. You don't have to do that, but it just might look easier. So okay, so now remember we substitute a in, so we don't substitute in u because those are our limits. So we get u over 2 evaluated between u equals 0 and u equals 1. So step 5 is substitute in, so we get the arc sine of 1/2 minus the arc sine of 0 over 2, which is 0. And now we evaluate this. So again, you can use a calculator for this, or you can, if you remember the unit circle, that's great. I'll just, as a review, remember how we do that. Remember that the sine of theta is equal to y, the cosine of theta is equal to x. So here's when y equals a half, because it's sine, we go over here and we find the intersection of the unit circle. And it's going to be, if it's a half, square root of 2 over 2, and square root of 3 over 2, it's going to be one of those nice angles. And because this comes over here, you can see it's about a third of the way around here. This is pi over 2. If you go 90 degrees, so it's about a third of that, which is pi over 6. So the answer is pi over 6, and the arc sine of 0 is 0. So we just get pi over 6, the second part. And because the first part of the answer was in decimal form, I'm just going to figure out what pi over 6 is. So pi divided by 6 is equal to 0.5236. And if I just did the inverse sine using the calculator of 0.5, I would get 0.5236 minus the arc sine of 0, which is 0. So either way, you get that. Okay, so now, what do we do next? Well, we add the two things together. So the first part was 0.5359. So the total integral that we started with, I'm not going to rewrite it, is 0.5359. 0.53, what was it again? 5. Way back here, 5359. Plus the second bit, which we just calculated, was 0.5236. It's amazing how close those numbers are, but it's just a coincidence. 0.5359 plus 0.5236 is 1.0595. So that's the integral, was the original equation, the integral of 2x minus 3 over the square root of 4x minus x squared between 2 and 3. And I just checked to see if that's correct. 39. 1.059, which is what I got. Okay. And let's just look at this function. Looks like a crazy function, but so I'm going to open up the graphing program. We're going to plot that and just prove it's about 1, because that's the area is about 1. Okay, so there's the graphing program, and if we just write this down, we get 2x minus 3 divided by square root of 4x minus x squared. So that's the function, and we're going to go from x equals 2 to x equals 3, and we graph it. So you can see it's not a straight line, but it's pretty close to a straight line. If you go halfway in between, you get 1. So if I were to draw the average value, which would be 1, I would get, this is 1 unit wide, this is 1 unit high, which would be about 1. And our answer is 1.059. So it doesn't make sense. This part, if you took this area, it's going to be less than, it's going to be less than a half, and this one's going to be more than a half. And when you add them together, it's going to be a little over 1. So it doesn't make sense that is what's going on. Okay, so I think that's all there is to it. If you survive that one, then you're in pretty good shape. Okay, so here's the last problem of the semester. It's problem 47. And what it says is determine which of the integrals can be found using the basic integration formulas you have studied so far. So 47a is the integral of 1 divided by the square root of 1 minus x squared dx. So is there a way that we can rewrite this and so that it fits? Well, yeah, if we let u squared equal x squared, and if we let a squared equal 1, then u is equal to x, a is equal to 1, du is equal to dx. And so this can become the integral of du over the square root of a squared minus u squared, which means that you're going to get inverse sine. So yes, you can do that one. The second one is x divided by the square root of 1 minus x squared dx. Okay. So, earlier on we said you always look at what's in terms of the what's inside of a radical or a parenthesis. So if we were to choose u is equal to 1 minus x squared, then du would be equal to negative 2x dx. And so we could solve this. We'd say that x dx is negative du over 2 by dividing both sides by negative 2. And at that point, we could rewrite this as the integral of negative 2 du. Oh, I'm sorry, I got the wrong place. It would be negative du over 2 and 1 over the square root of u. So if we factored out the negative 1/2, we'd have du over the square root of u, which we can't solve. So yes, we can do that one. The final one, I don't think we can do. Actually, I think we can do the final one too. So in this case, we would let u squared equal x squared. We would let a squared equal 1. So u is equal to x, or x is equal to u is the substitution we're going to use. And then a is equal to 1. So with that, we would rewrite that, and also dx is equal to du. So we get dx becomes du, x becomes u. We get the square root of a squared minus u squared. And so the answer of that is going to involve the inverse secant, or the arcsecant. So yes, we can actually solve all of these equations. Now if we had like x squared over the square root of 1 minus x squared, we couldn't do that using what we have right now. We can solve that, and we'll learn how to solve that in Chapter 8, but for right now, these three we could solve. So let me just check to make sure that's right. Oh, I'm wrong. Okay. So this doesn't work because what we have is, that's the tricky part. This part here, tricky. This is a squared minus u squared, whereas if you look at the formula, it's actually the square root of this. It's u squared minus a squared. So right now we can't do that. We'll be able to figure that out in Chapter 8. So no, this one you cannot do. So you got to be careful about the sign. It's like this. If we had x squared minus 1, we couldn't do that here, but we can do 1 minus x squared. So you got to make sure that they're in the right place.